Right, so notice that the x-intercepts were the same for all three equations. So f of x equals 2x squared plus 8x plus 6, f of x equals 2 times x plus 3 times x plus 1, and f of x equals 2 times x plus 2 squared minus 2. All have the same x-intercepts. I wonder why. So on this first one here, I'm going to factor. Right, so come on. Come on, little f. There we go. All right, so we're going to factor this first one. We'll use factor by grouping. All right, so to factor, first thing I need to do is factor out my greatest common factor. All right, so I have a GCF that, oops, that looks like GCE. And I was trying to make an equals and it looked all funky, so I'll just drag it up there. All right, so we're going to factor out a 2 from all of these terms. And so the 2 is going to go in front. Right? And I'm just going to put a little arrow here because that I'll pick up the 2 a little later on because I want to factor the leftovers. And then we know we have a factor of 2 in front. All right, so if we divide 2x squared by 2, we have x squared. If we divide 8x plus 2 by 2, we have 4x. And if we divide 6 by 2, we have 3. And you're right, remember that we solved something similar, but I'm still going to do the steps here. All right, so a times c, right, would give us 1 times 3, which is 3. So we need two numbers that multiply to give us 3, but add to give us our b term of 4. And of course that would be 3 and 1. All right, so now I have x squared plus 3x plus x plus 3. And the first two are a group, and the second two are a group. And our greatest common factor for x squared and 3x is an x, so we'll factor that one out. X squared divided by x is x. 3x divided by x is 3. X and 3, their greatest common factor is a 1, which is good because now it matches the other factor. So now we factor out our repeating factor. So we'll divide both of those by x plus 3. And when we divide those two terms by x plus 3, we're left with the leftovers, x plus 1. All right, so now we're rewriting the equation, not solving. So I'm going to put the f of x back. And my 2. Well, gee, that looks a little familiar. That looks just like, oops, there we go, the equation that is right below. F of x equals 2 times x plus 3 times x plus 1. These two match. Look at that. Well, now what happens if I were to multiply the x plus 3 times the x plus 1 and then distribute the 2? What would we end up with? All right, well, let's find out. All right, so we have f of x equals, all right, I'll deal with the 2 later. First, I need to multiply the other ones. I really don't want to distribute the 2 until I've multiplied the other 2. All right, so I'm going to multiply the x by x plus 1. So we're going to use multiplication by distribution. So the x gets multiplied by x plus 1, and the 3 gets multiplied by x plus 1. And that way we make sure that we have multiplied everybody by each other. And then we'll distribute the 2. All right, so that's going to give us 2 times, well, x times x is x squared. X times 1 is x. 3 times x is 3x. Oops, let me put a plus in there. What happened to my plus? And then 3 times 1 is 3. And if you notice, that looks just like, except I have them in reversed order. But notice it looks, the middle terms, notice it looks just like that, right, before we put the parentheses in, right, with the x and the 3x just switched. Right? And then, let me close my parentheses. All right, now I'll combine the like terms, which is 2 times x squared plus 4x plus 3, which looks just like the step above it. which is what factoring is, right? It's just undoing multiplication by distribution. All right, and now distribute the 2. So we have f of x equals 2x squared plus 8x plus 6. And notice this is the same as that. Those match. So all these two equations here, 2x squared plus 8x plus 6, and f of x equals 2 times x plus 3 times x plus 1, are two different equations for the exact same function. Let's take a look at the 2x squared plus 8x plus 6, and we're going to rewrite using completing the square. By the way, you can't use quadratic formula to rewrite. I can rewrite by factoring. I can rewrite by completing the square. All right, so to rewrite using completing the square, right, I'm going to leave that as an f of x because I don't want to solve, I just want to rewrite. And we're going to subtract 6 from both sides, right, because we want to get the x alone, right? And then we're going to add that special number. So we have f of x, actually I'm going to move that 6, by the way, before I divide. So we have f of x minus 6 equals 2x squared plus 8x. But before I divide is because when I divide, I can't get rid of anything. Right? If I'm rewriting, I can't get rid of anything. Otherwise, I have a different equation. Right? So we have f of x minus 6. So I'm going to factor the 2 out of these two terms. And I'm going to leave the 2 right there. So I have 2x squared divided by 2 is an x squared. 8x divided by 2 is a 4x. Now we're going to add our very special number, right, which is b divided by 2 squared. Right? And we're going to have to add it to both sides. So we have f of x minus 6. I'm going to leave a space. Equals 2 times x squared plus 4x. I'm going to put it right there, the missing number. Right? So b divided by 2 is going to be, so b is 4 here, is going to be 4 divided by 2 squared. However, is that really 4 divided by 2 squared? Well, no, because there's a 2 right there. Right? So if I distribute that 2 back, that's not 4 divided by 2 squared. It's 2 times 4 divided by 2 squared. So I have to make sure on the other side over here, I add in 2 times 4 divided by 2 squared. Right? Now I've added in the same thing to both sides. Right? Because if I distribute that 2 back, that is no longer 4 divided by 2 squared. Right? So now I have f of x minus 6 plus, well, 4 divided by 2 is 2, and 2 squared is 4, equals 2 times x squared plus 4x plus 4. Right? So technically, right, have I now added in an 8 to the right-hand side? Absolutely. So I have to make sure I add an 8 to the left-hand side. So when you're rewriting these, if you factored out a coefficient, right, you have to remember to, when you add to the other side, to multiply that value by that same coefficient. All right, now let's clean this up. So f of x, so negative 6 plus 8 is going to give us a positive 2. So we have f of x plus 2 is equal to 2 times, let's factor, x squared plus 4x plus 2, we know it's going to be, with our completing the square, because that's a perfect square, it's always going to be x, whatever the sign is, of b, so it's plus, and then half of b, the thing you squared, right? Or half of b, however you want to think of it. So this would be x plus 2 squared. Now, I need to solve for f of x, so I'm going to have to subtract 2 from both sides and put it back. It's much easier to move it out of the way and then move it back than try to keep it off to the side, you know, at the other end of the equation, while we're trying to rewrite the right-hand side into a perfect square using completing the square. So now I have f of x equals 2 times x plus 2 squared minus 2. Hey, that looks familiar. And that's because these two match. Look at that. It's the exact same equation in vertex form. So when we rewrite using completing the square, we turn it into vertex form. What would happen if we were to expand that square, distribute the 2, and add the like terms together? Let's find out. Right, so we have f of x equals 2 times, so x plus 2 squared is not x squared plus 4. It is x plus 2 times x plus 2. And we have minus 2. All right, so f of x equals 2. Let's use multiplication by distribution. So I have an x times an x plus 2, because I got to multiply everybody by everybody else, and a 2 times x plus 2. Right, now I'd have 4 products, right? I've multiplied everybody in the first by everybody in the second. And then we still have a minus 2 out there. All right, so we have f of x equals 2, and then x times x would give us x squared. X times 2 is 2x. 2 times x is another 2x, and 2 times 2 is 4. That negative 2, that is not multiplied by 2, only the x plus 2 squared was. Let's combine the like terms and then we'll distribute. So f of x equals 2 times x squared plus 4x plus 4 minus 2. So we have f of x equals 2x squared plus 8x, right, because we're distributing the 2, plus 8, and now I can drop the parentheses because I've already done the multiplication, minus 2. I combine my like terms, and f of x equals 2x squared plus 8x plus 6. And hey, that means that this, and this match. So look at that. Any way you go, whether I change it from vertex form back to standard form, whether I change it from standard form to vertex form, whether I change it from intercept to standard form, or whether I change it from standard form to intercept form. Any way you look at it, it's the same equation. Right? So these three are just 3 different equations that represent the exact same graph. Any quadratic graph of a quadratic equation, any quadratic equation can be represented in the 3 formats, either in vertex form, or actually I should say any of our quadratic equations can be represented in vertex form or standard form. You can always write any equation into either vertex or standard. If it's factorable and it has real rational solutions, then you can also write it in intercept form. If the solutions were complex and we could not factor the 2x squared plus 8x plus 6, then we could not write it into intercept form. Right? So only our factorable, only our quadratic equations with real rational solutions, real rational x-intercepts, those can be rewritten into intercept form. Otherwise, you can always write it in standard or vertex. So these are all the same graph. So let's graph this same graph. Once we have all, and this is in your notes, once we have all of our information, the axis of symmetry, the vertex, the y-intercept, the x-intercept, our equation is easy to graph. You're going to graph the points. You're going to make sure it looks like a parabola. You're going to find all your information. You're going to graph it. Make sure it looks like a parabola. If some point does not, all of a sudden it doesn't look like a parabola, one point is off, don't try to make it into a parabola. Figure out what's wrong with that point, because something's wrong with the point. These are very symmetric. The right-hand side looks exactly like the left-hand side. So if something doesn't look right, see what your mistake is. Maybe you just graphed the point wrong, or maybe you made an error. All right, so the axis of symmetry, if we go way back to the beginning, all right, here we go. How fast will this go? Bump. Actually, let's pick up we'll just keep going. So we'll go all the way back to the beginning, and then we'll pick up all of our things. I just wanted to remind you of everything we solved for. And the first thing we solved for was the y-intercept. And actually it doesn't, I'll just stop at the first time we found the y-intercept. And that's not it. One more. Wait, I think two more actually. There we go. This the first time we found the y-intercept, it was 0, 6. It was 0, 6 for all of them. All right, so that's the first thing we're gonna put in our graph. 0, 6 is the y-intercept. Now let's go ahead. All right, so here we have the equation in standard form, and we found the vertex is -2, -2. The axis of symmetry is just a vertical line through the x-coordinate of our vertex. This was another equation. So our axis of symmetry was -2. X equals -2. There it is right there. All right, so we've got our vertex, we've got our y-intercept, and then 3 different times we found, there's our vertex again, our axis of symmetry, but 3 different times we found the x-intercepts. -1, -3. There they are, once, twice, and this had nothing to do with it. That was just showing you the steps one more time. 3 times. There we go. All right, so let's put that on our graph. Now that your memory's been refreshed, all right, this was x equals -2. It's already on our graph. Already put it on there. All right, that's that yellowishy line. So you graph that. It's very helpful because then you can see it's very helpful for finding additional points, and I'll show you that in just a moment. We know what the vertex is. The vertex was -2, -2. The y-intercept was 0, 6. The x-intercepts were -3, 0, and -1, 0. And then we'll talk about domain and range in just a moment. So let's just graph our points. All right, so the first point I'll graph is the vertex there, right on this axis of symmetry. Right there's our vertex. Let's label everything too. So vertex, -2, -2. And then we have an x-intercept right there at -1, 0. That was an x-intercept. We have an x-intercept on the other side of the axis of symmetry. And that would be -3, 0. So you see how symmetric this is. All right, those two x-intercepts, exact same distance to the right and to the left and vertically from our vertex. We have a y-intercept at 0, 6. Right here, right? Make sure I'm looking at the right. Okay, they hardly look any different, these black lines, but the one with the x-intercepts is slightly blacker. 1, 2, 3, 4, 5. I mean, that's only a 5. Sorry, I only counted up 5. That's why I wanted to check. Sometimes my shadow is blocking me, and so I want to make sure I was in the right spot. 1, 2, 3, 4, 5, 6. Very good. So now you see we have a point 2 to the right and 6 up. This is very, very symmetric. We have to have a point 2 to the left of the axis of symmetry and 6 up. So there has to be a point here too. All right, so that's the nice thing about using your axis of symmetry. If you've got a point to the right, you've got the same point to the left. And whoops, same point to the left. There we go. All right, so this point here is our y-intercept, and that's the point 0, 6. The other one was a bonus, nothing special about it except for it's a bonus point for us, and that's at -4, 6. Right? So same distance away from the axis of symmetry, but on the other side. Now all I have to do is connect my points with a nice smooth curve. Try to make it not look like a V. It's not V-shaped. That's a different kind of graph. That's absolute value. Right? It's U-shaped. Do your best. Right? And so that looks pretty good. And notice how symmetric my graph is. Domain and range are really super easy. Every single time your domain is going to be -infinity to infinity. Remember we found domain and range for linear functions, and you can plug in anything you want for x, whether it's a linear function or whether it's a quadratic function. There's nothing I can't square, no number I can't multiply, a coefficient by. So our domain is all real numbers, right? This is not going to stay at the points we graphed. It will keep going out farther and farther and farther. There's no reason for us to graph more points. It fits very nicely on our graph, and we've got enough graphs shown to give the shape and all, but this is going to keep continuing going out farther and farther and farther, well beyond the limits of our graph that we have here, the coordinate plane that I'm showing. The range is not going to be all real numbers. It is restricted. Why is it restricted? Well, because when you square negative numbers, you get positive numbers. Notice the parabola turns around, right? It doesn't keep getting small. The numbers don't keep getting smaller and smaller. It goes back the other way, right? It gets to the vertex, goes back the other way. So the y value of our vertex is either going to be a maximum value or a minimum value. If your parabola is facing concave up, it's a minimum value. If your parabola is concave down, it's a maximum value. In the other direction, in this case, -2 is a minimum value, and our graph does go through -2. So we're going to use brackets. So the brackets, so add this to your notes, brackets means that that value is in the domain or range, as the case may be. All right, so that it is part of it. Right? You can't, so negative infinity, infinity, they don't get a bracket. You can't get to negative infinity, infinity. That's a concept that just means increasing forever without bounds, or decreasing forever without bounds. But -2, my graph goes right through -2. It's the vertex. So get in the habit of using a bracket when that value is actually a point on your graph. Now, notice that both ends of our parabola are going up. They'll go up forever and ever and ever. They're not stopping at the last 2 points I graphed. I'm just pretty much have run out of space on that graph, on that coordinate plane that I have. So -2, it's going to keep on going forever and ever to infinity. And now I use a parentheses, because parentheses means that the value is not in the domain or range. Or it's not a value at all. Right? Or not a real number. So infinity is not a real number. It just means increasing or decreasing without bounds, depending on which way you're going. All right, so we'll notate that correctly. All right, and that's all there is to graphing. Right? We're going to do a few more graphs. Some of our graphs are going to have so actually, I'll talk about it on the next page. So but this is all there is to graphing, really. You just need to find your axis of symmetry and your vertex. Will always have an axis of, a parabola will always have an axis of symmetry, a vertex, and a y-intercept. Sometimes it might not have x-intercepts, and we'll always be able to find the domain and range. And the domain is never, ever going to change, and the range just depends on what the vertex is. All right, one last slide I want to look at. So some notes on quadratic functions. The graphs of quadratic functions are parabolas. The solutions that you'll be looking for are the x-intercepts of the parabola. Sometimes there are no x-intercepts, but there will always be 2 solutions. The x-intercepts are also called the roots, the solutions, or the zeros. Quadratic functions can have 1, 2, or no real solutions. If you have 1, it means it's repeated. And we'll talk about what repeated means in terms of our graphs a little bit later on in this lesson, as well as in a future lesson. Quadratic functions that have no real solutions have complex imaginary solutions. Right? So now you can do the whiteboard practice, which is not going to involve you graphing, but just reviewing how to find all of our different features. Right? The direction of a parabola, the y-intercepts of a parabola, the x-intercepts, and the vertex. All right? And I need to make sure that I never used any of these on the Nearpod lesson before I post them. So don't pause the screen to do it unless I tell you you can do that. Otherwise, just look on Schoology and you'll find those there. All right, thanks for watching this podcast. Bye for now.